Welcome. This is going to be the first video in a series on mathematical methods in the physical sciences. That name, it might be a little deceiving. What I really prefer to call this is a series of lectures on better understanding physics and mathematics. That's quite a broad topic, but that's what we're going to do today. So we're going to basically, this video series is meant for someone at the freshman, sophomore level of physics in college. But of course, you could do it earlier for an introductory or later for a little review. And it's going to, in the series, we're going to talk about a lot of problems, and we're going to follow the book by Boas just roughly, but we're also going to add a lot of numerical and computational methods and problem solving on top of that. So let's go ahead and get started with this introduction. And I'll be using this setup and showing you a screen and some paper. So in general, this is typically called mathematical and numerical methods in the physical sciences. It's a long name, but really we're just trying to understand mathematics and physics both together and how they're related, how we can better solve physical problems by understanding the mathematics behind them, right? So one problem that we often find in physics is that all too often people try to memorize, right? So we definitely do not want to memorize. So for example, you might memorize x equals x naught plus v naught t plus 1/2 at squared. Great. You've memorized that, but what does it mean? When does it break? When does it work? When can you do something simpler? When do you have to do something more difficult? If you just memorize this, you don't really understand when it's going to work and when it's not going to work, right? So we're going to try, of course, to not memorize. We're going to search to understand, right? And we find that this is not just trying to learn new mathematics. You typically find that by understanding the math, right, that this also helps you understand the physics, right? So remember, calculus was basically invented or discovered, depending on how you want to look at it, by examining physical situations, right? So the physics tells us about the math tells us about the physics. So we want to be able to easily translate between the two, math and physics, all right? And in these lectures, we're going to also focus on applications. So we're not just going to learn new techniques, of course, we're going to apply those techniques, right? This is going to help us actually understand them by being able to apply them, okay? And in general, another way to say this is we want to be fluent, right, in this translation, right? We want to be good translators between math and physics, all right? So typically we have some kind of hierarchy, like we're given a problem, right? Or you find a problem or you want to understand something better, right? As you move on in physics, you'll find out that problems aren't just something teachers prescribe to you. They're things you come across. They're things you want to understand, right? And typically in physics, then we want to make a model, right? We want to make a model, right? And if you've had some physics, this could be something like a free body diagram, right? And once you make a model, right, then we usually think about the mathematical techniques we're going to use to understand that problem, right? So if we had a free body diagram or momentum conservation, then we'd know the mathematics we were going to use. But realize this can also flow the other way. Sometimes we change our model depending on what math is easiest, right? So if we have something spherical, we might use spherical coordinates, right? So it's not like you don't change the model depending on the math, all right? And then once you have the math, then there's also different things. So you could do analytical, you could do numerical, you could do computational. All of these are acceptable ways to solve a problem, right? And this is really the choice. You want to be fluent in all of these. And a successful physicist is going to be fluent in all of these because often the answer is not one or the other. The answer is all three. We do the analytical part until the analytical part is not practical anymore. Then we do a numerical part, right? Then we do a computational part. Maybe inside here we make an approximation. And then we do something numerical. And then we apply that numerical to computational, right? All with the idea we want to solve this problem, right? And we want to solve this problem, and almost when you do an approximation, right, we want to know what this approximation means, right? So it's not just enough to do approximation, but we have to think about when that approximation breaks down. All right. So that's the broad overview of what we're doing in this series. So specifically what we'll do, I'll just write some of these down so you get an idea if this might be interesting for you. We'll look at series, right? So for example, Taylor series expansions. And remember, series are also the foundation of calculus, so these are important things. We'll look at complex numbers, right? So again, to try to understand these, not just be able to use them, but when they're applicable to use. We'll look at linear algebra, right? So how can I translate my problem into matrices and vectors if that's applicable, right? We'll look at vector calculus. We'll look at also a bunch of numerical techniques and a bunch of computational techniques. And finally, we'll end with some hopefully interesting special topics. And hopefully we'll combine. So we'll try to combine all our knowledge to solve real problems. So we'll go back over here to page 1 and basically start with something we want to know the answer to, right? And then apply all those techniques that are necessary to get to the answer. So we'll go ahead and get started here with some examples. I find that Physics 1 at the college level, or if you took it in high school, AP Physics, is somewhat deceptive. Most people think that they know if you ask them, for example, they would say, if you say, do you understand calculus-based physics? They would say yes. But most of them don't understand the calculus-based physics, unfortunately. Maybe every once in a while the professor writes an integral up on the board to find some proof, but they go back to something like this, right? Where delta x equals x naught plus v naught t plus 1 half a t squared, right? So they kind of memorize the algebra, but they don't understand the calculus that is behind the scenes. So, for example, let's think of a typical example of this. So an example, and I'm sure this is something you've all covered, is simple harmonic oscillators, right? So you have a pendulum, and this pendulum goes back and forth, right? And if you've had a good physics class, right, so let's call this distance L and this mass M, right, and you can even draw the free body diagram, right, so if I have the mass here, realize that I have mg coming down, and I can draw this as two component vectors, this way, and talk about the angle theta, and I will call it the angle phi just to be consistent, right? So we have this angle phi. And if you've had a good physics class, you've covered this, and you know what the answer is. You know that somehow theta equals cosine of omega t, right? You know it oscillates back and forth, so you know if I plotted this in time, it's going to do something like this, okay? If you've had a very good class, you know that omega equals the square root of g over L, where g is the length of the pendulum, g is gravity, of course, L is the length of the pendulum arm, and it doesn't depend on the mass that's on the swing. And you know that you can pull it back to different lengths, right? And so theta, and again let's call this phi. So phi of t equals some amplitude times cosine of omega t minus, let's call it phi 0, right? And this depends on where you let it go. That's great. That's some knowledge, but you don't really understand the system For example, if you just memorize this, you might not realize that this is just an approximation, right? This is right? You might just write these equal sign, but this is not true. This is an approximation. And since it's an approximation, that means it breaks sometimes. And when does it break? Where does it break? Why does it break, right? That's some of the things we'll be interested in this class. Is where does it break? When can I not do this anymore? Why is this an approximation, right? And so if we dig a little deeper, right, we could do the free body diagram here, right? And so which part is pulling this way? We have mg sine of theta, right? That's the force in this direction. And that force is just going to equal the mass times the acceleration. And the mass times the acceleration is just m, let's see, L theta double dot, right? This is another way to say F equals ma, right? And of course, hopefully you've seen the concept that a is just the second time derivative, right? So a equals dv dt equals d squared dt squared dx. And in physics, we often write this as x double dot, right? This is just a quick-hand way of writing the time derivative. All right. So now that we have, or you might have learned torque, right? So you could also write torque equals I alpha, right? And in this case, we could also write the same kind of equation for torque equals I alpha. Torque equals R cross F. So this on this side is just going to be L mg sine theta equals ml squared, right? Moment of inertia is ml squared times, and we needed a theta double dot on this side because alpha is just basically theta double dot. Okay, you see that I've done multiple ways, but both of these are going to give me the same answer. Namely, I'm going to get that theta double dot equals g over L times the sine of theta. All right. So this is the real answer to this problem. This is the differential equation that describes what's going on. Realize that even this is an approximation. Even at this point, I should say things like no wind resistance, no dot dot dot, right? So it's inside a vacuum. There's no wind resistance, right? There's no friction. There on this turning point here. There's all kinds of little assumptions that are also going on there. So even making it to here, there's several assumptions that are going on. But what other assumptions do we have? Even if we start from theta double dot equals g over L. Well, that's where it's handy, right? This is not a simple, well, it's not a trivial, at least, differential equation to solve. What we'd really like to solve is the trivial differential equation, theta double dot equals g over L times theta. All right. So if we have theta double dot equals g over L times theta, this is just saying the second derivative of a function equals the function itself, right? So what did I do to get this equation? Well, I'll just solve that here first. Realize that this gives you back the same thing of a times the cosine of g over L square root t plus theta 0, right? This is a solution because the first derivative is going to give you this. Of course, there's a minus sign here that I've dropped, right? But this is going to give you the correct answer, right? Because the derivative is going to pull out the g over L the first time, and then the second time it's going to pull out another square root of g over L, and so that's how you're going to get g over L on the outside. But realize the move I've made, right? The move I've made here is to say the sine of theta is the same thing as theta, okay? Why is that the case? How is that the case? That's just by doing a Taylor expansion, right? And this is something we'll talk about in the next lecture. And we can find that the sine of theta equals, right, theta plus, well, in this case, actually minus theta to the third over 3 factorial plus theta to the fifth, dot, 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 dot. All right? So we're making an approximation. So when does this approximation work, and when does this approximation break down? Well, notice that if theta is small, right? If theta is small, then theta is going to be greater than theta to the third, right? If theta is 0.1, then this is 0.001, right? So this is smaller. But if theta is big, right? So if theta is 2, then obviously theta to the third would be 8, and this is bigger than 2, right? So we have to look at when these break down, all right? And if your professor or instructor was good in this course, they might have even used the word small angle approximation. Why is a small angle approximation? Well, because it only works in this situation. So if theta is small, then it's acceptable to say the sine of theta roughly equals theta, and then we can go back all the way here and use this solution. But you have to understand the physics in order and the mathematics to understand what that means. All right, and we can give a little example of what's going on here. Perhaps it's even better to start before we give an example is to think about why this works, right? Let's think about the pendulum in this case, and let's not think about it just going back and forth down here. Let's think about what happens if I would put it all the way up here and assume that this is not a string, assume this is a solid rod, all right? So we have mass and we have this, all right? What's going to happen? Well, you're going to spend a long time up here top, right? You're near an equilibrium. So instead of just oscillating back and forth and back and forth and back and forth, when you're near the top, you're actually going to spend a long time and then slow and then go fast, right? So slow, 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 and then fast, and then back up here, slow, 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 and then back fast, right? So you're going to go slow and then fast and then slow and then fast and then slow and then fast, right? When this is a graph of time versus angle. So how do we quantify that? How do we know when it's good, when it's not good, right? So mathematically, we might even say something like the sine of theta equals theta plus, and we write it like this. Unfortunately, my order, this should look like a capital O. Things on the order of theta to the third, right? So this just says, we're going to say it's this, but we notice that there are terms like this that are hanging out, all right? So we're going to switch over now for a second, right? We'll pause. And now we're going to switch over and look at another thing, and don't get too distressed if you don't understand every little thing I'm doing here. This is just to give you again an introduction, and we'll go in detail on all these things, right, during the course. But so for example, it's nice so we can just do this numerically, all right? So for example, this is Octave. This is a free program. It's in some ways a clone of MatLab, but it's a nice program because it allows you to get to functions and plotting very quickly, right? So the nice thing here is I'm just going to define a function that acts like a pendulum. And namely a pendulum, remember, we had theta double dot equals minus g over L theta. That's all this is saying, right? So all this stuff, right, is just part of the program we'll go over, right? Bookkeeping, right? Programming is a lot of bookkeeping and usually not that much actual physics or programming, right? So this is the physics that's going on. Whoops. So this is the only, line 9 here is the only physics that's actually going on. It's saying the acceleration equals minus g over L times the position, all right? And so then I can define g and L. I'm just going to make it 10 and 10 just to make it life easy. These are not real numbers, right? This would be 30 feet long, and gravity is not 10, it's 9.8, but close enough for what we want to do. And we can define things like the initial position, the initial velocity, and the time span we want to go, right? And then I can just say, solve this. ODE just means an ordinary differential equation. So solve the ordinary differential equation and show me what it looks like. All right. And let's see. Oops. All right. All right. My computer's a little grumpy. Running video capture at the same time. Oh, there we go. So this is actually quite quick. This program will run almost instantaneously. So when we do this, we see here on the graph, hopefully you can see this graph, I'm plotting time in periods just to make it simple. So this is 1 period. And you can see that it just bounces back and forth in time and makes a simple approximation, all right, of what's going on. So we have this approximation. It goes back and forth. But you can see that if I change some parameters, you'll see that it quickly begins to break down. So for example, if we start this, if I change my initial conditions to 10, or let's make it 3, right? So this is in radians, of course. So this is starting almost straight up, right? So if we go to 3, you see that it didn't care, right? So even if I start near 180 degrees, right, this plot is showing the theta. So I started with the pendulum almost directly straight up, right? And I let it go. It's still a nice sinusoidal oscillation. But of course, this isn't true. We've already thought about this situation, and it should pause at the top of basically at the top. So let's go back, and we can add another function here, right? And this is a more realistic function. So now the acceleration doesn't equal, so theta double dot doesn't equal theta, it equals the sine of theta, right? So now this is the real calculation that's going on. And I'm going to go down here and I'm just going to make these plot, and I'll comment out the old plot. Again, don't worry too much about the specifics that's going on here. All right, let's run that, and we can see now we have the approximation and the real solution, and you only really see one here because they're so close they're on top of one another. All right, so, but that was with very small initial conditions. If I change this to 1, now we can start to see a difference. Now I started it off near 60 degrees, and if I start it near 60 degrees, you can see now that the real solution, actually, it takes longer at the tops, right? So it's out of phase about what's going on, right? And if I change this to something like 3, you can see it gets much worse, right? So this approximation breaks down in this case, okay? So we have this approximation, and this allows us then to say when it breaks, where it breaks, and we can do the real thing versus simplified things, right? And we can start to quantify how much it breaks down. We could also do things like here and say, well, this is the first order approximation. What if we added a little bit better? Now I'm adding the next order approximation. So what does that do? Well, let's change this a little bit so that it goes better. Let's say that this is 2. And you can see, oh, wow, okay. So just adding the next order approximation actually made it a lot better, right? So you get in a situation now that you understand the mathematics and the approximation where you can say, well, I can use the very simple things, let's say if I'm less than 10 degrees. And if I'm bigger than 10 degrees but less than 40 degrees, maybe the next higher order approximation is enough. But if I go past some other mark, then I need the full treatment where I treat this really like the sine of theta. Okay? And I grabbed the wrong thing there for a second. All right. So really like the sine of theta. All right? So we'll learn how to also do this kind of computational work, and we'll learn how to do these plotting so you can actually do these kinds of things. And you'll find in this course that it's a disturbing amount of physics is captured within this. All right, sorry about that. We had a little bit of a computer glitch, but I think we're doing fine. So you can see some of the things we'll do by understanding what the approximations are, treating it numerically, and all I was going to say is that a disturbing amount of physics 1 can be done like this, right? Where you just define the physics involved and let it be solved numerically. But of course, analytical solutions certainly still will have their place. All right, so let's look at another problem just to drive home the point here. So let's go back to the paper. Good. So if we go back to the paper, we can look at another problem. Maybe will be helpful to drive home the difference in this course and the courses you've probably taken before. So let's square this up. So when we understand vector calculus, right, we'll actually find a lot of interesting things that's going on. So again, you think you've done calculus-based physics, but you probably really haven't done calculus-based physics if you've had college physics 1 and 2. So for example, let's actually look at a problem like this. So let's say, well, why not? So let's say y equals x squared. Let's say that this is the side of a hill, right? And I want to know how much work is done by climbing up the hill. So we already know the answer. Work equals mgh is what you'd say, right? And so if I climb to some distance x, this is just going to be mgy, and this is just mgx squared. That's fine, that we already know the solution. Just realize that this will work in situations, for example, maybe it's not gravitational potential, maybe it's electrostatic, right? Maybe it has some other form. So it's always good also to start with problems you know the answer to see if your methods are correct. So if this is the answer, it's better to remember that, well, so don't memorize, right? So we don't need to memorize for certain situations. It's better to understand the basics, right? So remember, work equals the integral of force dotted with distance, right? And depending on if this is a potential, you might want to write a minus sign here. All right, that just tells you if you're doing work or work is done upon you. So we have this integral, and you notice that there's vectors inside this integral. And you notice also that if you do this right, this is what's called a path integral, right? I have to move along the path, right? And this is a strange concept because moving along the path, we notice that like if we do our calculus, in this little part, ds doesn't point in the same direction, right? So in this case, ds, right, actually equals the square root of dx squared plus dy squared, right? Yikes. Right? If you're not used to vector calculus, this is going to be a very disturbing situation for you. You have an integral now with dx and dy squared, and the differential element is under a square root sign. Wow, that's not going to be fun. Okay? So we'll learn some tricks, and this is an example of one of the tricks. And sometimes a trick, a good mathematical concept is actually, you'd make it slightly harder or introduce a new concept that makes it easier in the end. For example, an interesting concept is, remember that the position we're at, right, equals the velocity times the time, all right? So instead of trying to climb up this hill, as it were, right, remember in this situation I can think of myself climbing up this hill and finding out how much work I have to do to climb up this hill. We can instead think of this as a time-dependent problem where I'm walking up this hill in a certain amount of time, okay? So if I'm walking up this hill in a certain amount of time, then instead of this integral of the integral of ds, right, I can translate this into the integral of v dt, all right? Because of course your velocity just equals ds dt, right? So this might seem like a strange problem. I have a problem that has nothing to do with time. It doesn't care how fast you got to the top of the hill. This doesn't even matter in the problem. So why should I introduce time? Well, introducing time is going to actually make my life a lot easier because I can describe what velocity is a lot easier in some situations than I can describe what this ds bar is, right? This vector ds. Notice I got the vector part out of the differential, right? The differential element. So for example, where am I at this point? Well, I get to choose my time. I get to choose how fast I walk up the hill. So let's just say I walk 1 unit in x in a time dt. So my position, right? So I'll just call my position r. My position r equals, well, I get to choose how fast, so I'm just going to say t in the x hat, right? So this just means I'm walking constantly across there. But if I'm walking constantly across there, it's going to be t squared in the y hat. All right? That tells me how fast I'm walking up. You might even write this as a vector t squared. All right? Well then, what's r dot? Remember, this is just the velocity by definition. Well, the velocity is just the derivative, and this is just x hat plus 2t y hat. Or another way to say this is 1, 2t. Okay, fair enough. So now we have our velocity, and now we can say the work equals minus the integral of the force. Well, what's the force? The force is pointing down, right? And the force is mg. So we have mg in the y hat, dotted with, and this is not a times, this is really a dot now, dotted with x hat plus 2t y hat dt, right? Integral from 0 into however long you climb the hill. So 0 to t, and it's typical that we make these t primes to just integrate, to just know that they're dummy variables, right? We're integrating, so from t prime equals 0 to t as we move forward. All right. So now this integral is not difficult, right? What's the dot product of x and y? Well, this goes away, so this just equals the integral of this times this. So it just equals mg 2t dt. Easy enough, right? That's the how a dot product works. What's the integral? Well, the integral is just mg t squared over 2, so it's just t squared. So the work is just equal to mg t squared. And you'll notice I've dropped a couple minus signs, so this is a minus here, and this one away. So I just get mg t squared. All right, and remember, we chose before that x equals t, so this is just mg x squared, or this is just mg y. Okay, so we got the same answer, or the answer that we were expecting, the answer that we knew had to be the right answer, but we did it in a different way, right? And we did it actually in a much more fundamental way, right? So we didn't have to make a whole bunch of assumptions, right? For example, this force could have been any strange force we wanted to. In this case, it's a conservative force, and that's why these moves all worked, and we'll learn about conservative forces during this course. But even if this wasn't a conservative force, even if this force had some frictional component or some kind of electromagnetic component that wasn't conserved, this process would work, right? And so you can see how understanding the physics is going to help you in understanding the math and vice versa, right? So we changed a problem that didn't have time anywhere in it to an easier, by adding what seems to be more complex, adding time dependent, actually make the problem easier to do, all right? So, and this is another way we'll use vector calculus in this course. These and understanding path integrals is going to be very handy in understanding and not being scared to deal with things like this, where you have vectors inside the differential sign, right? And also things like this, where you have multiple differentials or algebra working on differential elements. All right. So let's do one more problem just to show you, and this is not at all to insult your previous physics teachers or insult you or what you understand. Just realize that you have to start at some kind of starting point, right? So you know quite a bit of physics, right? But just realize all the approximations and assumptions you've been making, right? So if you were asked before you saw this, you said you might understand work energy, right? Or how forces work. But really you probably didn't actually understand or wouldn't be able to deal with a force that wasn't conservative. After this course, hopefully you will be able to deal with a force, any force, right? Conservative or not, because you understand the underlying physics. And more so, you can forget memorizing this because you understand how it works. And once you understand how it works, you can basically derive all the simple situations. All right, so let's do one more. So you've also probably had some E&M. So let's look at a problem. Here's a classical problem. So a classical problem is something where, let's say I'm above a ring of charge. All right, so this is a ring of charge. This has a radius of, let's say, capital R. This has a distance of Z. Okay, so in this case, right, so this is just an example. You've had a year probably or a semester of electricity and magnetism. You know how electricity and magnetism works. So could you solve this problem, right? And most people coming into this class couldn't really solve this problem, or it would be extremely difficult for them to solve the problem. Because probably you've memorized things from E&M like F equals KQ over R squared. All right, that's great, and that's the force from a point charge, but realize this is incomplete. The actual law is force equals KQ over R squared in the R hat. All right, this script R I'm using, that's basically the distance from the source point, so this will be my script R vector. All right, so this is the force, but that's just the force from one point. How do I deal with the force from multiple points? Well, in that case, right, I'll have to write the integral. So the force is going to be it's going to be the sum, but of course the sum is just the integral when it's continuous. So it's going to be the integral of k times dq over r squared in the r hat, right? So notice we have vectors again inside the integral. And we need those because if we look at our situation, this guy is going to have an electric field that points like this, whereas this part is going to have an electric field that points like this. So part of that electric field is going to cancel out as we move forward, right? And before we get started on this problem, it's helpful to even think what the solution to this problem is. So let's just assume, for example, this ring has a total charge of Q. If this ring has a total charge of Q, then my guess is going to be that in the limit as Z is much, much greater than R, so as I go far away in this case, my force should just go back to K big Q over Z squared in the Z hat, right? That's my guess of what's going to happen, because if I'm far away, it just looks like a point charge. So it's also not bad to use your previous knowledge to get an understanding of what the limits are going to be. So first of all, let's think about dq. Well, how much charge is in some little segment here? Well, it's spread out over this whole wire. What's the length of the wire? Well, the length is just 2 pi r, right? That's the length of a wire, so that just means dq is going to be q over 2 pi r d phi, right? Phi is just the distance around as we go around there. All right, so as we do this, now we can actually start to write our integral. So our total force is going to be k times the integral of, and I'm doing this part, dq is just q over 2 pi r d phi, right? But this seeming an innocuous little guy, right, is going to be the most difficult. So first let's think about the distance. So let's think about this. So what's the distance from this charge? Well, luckily it's a ring and we're in the center of a ring, so that's not bad, right? So this part was just dq, right? So what's 1 over r squared? Where r squared is just big R squared plus z squared, square root squared, so there's no square root, right? So this is just 1 over r squared. But now I need the vector part. So what's the vector part going to be? Well, I need which direction it's going to point, right? So for this part, it's going to point that way. And it's always good to think about what would happen if I'm on the x-axis. So if theta is 0 and I'm pointing here, it's going to point in the minus x direction, right? So I'm going to continue this on the next line. This is still inside this integral. So it's going to be minus cosine of phi in the x hat, right? So when phi equals 0, it's pointing in the x hat, that amount, right? And also, oops, we got a little problem here. All right, the computer's being a little bit fussy today. But, so we have the cosine of theta, and of course this describes what direction it points, but this is only part of it, right? We also need to worry about this angle alpha, right? And that tells us how much points there. So if alpha is 0, it's 0, right? So we also need the sine of alpha inside here, right, where this is alpha. Again, if it were straight down, there'd be nothing in the x, it would be all in the z, right? And we also need the y component, so we need minus the sine of phi in the y hat, and again we have a sine of alpha, right? We also need a z component, and I'm running out of space here, but the z component is going to be plus z in the z hat, and it's going to be cosine of alpha. All right, so let's go ahead and continue on. As we're getting, we're doing okay on time. So as we continue on, we can basically simplify this and realize that alpha, right? So again, here's our triangle, and here's alpha, right? And this is r, and this is z, right? And this is the square root of z squared plus r squared. So that means we can redefine the sine and cosine alpha as z, right, of z over the square root, and r over the square root. So that simplifies our force, and our force in this case is going to be k q over 2 pi r, and now I'm going to have the integral of minus the cosine of phi in the x hat minus the sine of phi in the y hat plus z in the z hat, all divided by z squared plus r squared to the 3 halves, right? And this 3 halves comes from this guy times this guy, right? So z squared plus r squared is z to the 2 halves, right? And then to the square root is another half, so 1 half plus 2 halves is 3 halves, right? And so this is our solution. This might not make you happy, but another thing we'll learn is that it's certainly fine. In this case, we can use something like, and we'll learn how to use Wx maxima in this course, right, as our problem, and you can use Wolfram alpha, there's other things. And so I'm just going to do that integral that we wrote. So I'm just going to integrate the cosine of, I used x instead of theta, it was easier to write. So integrate the cosine of theta over r squared plus z squared to the minus 3 halves, right? So, and from 0 to 2 pi, and I find the answer is 0. And I do the same thing from sine, and I find the answer is 0. And I do the same thing for z, and I find that the answer is 2 pi z over this thing to the 3 halves. Well, does that make any sense? Is that a reasonable thing to get? Well, the answer is yes, it is. So why is the x component 0? Well, the x component is 0 because, of course, it's a full ring, and so this part cancels out with this part, and when you add them together, it just leaves that part. So, of course, we should have expected all along that the x part is 0 and the y part is 0 if we have the full loop, right? And what about the z part? Remember, we had the idea before that this should look like a point charge. Remember our guess here in the limit. Well, does it? Well, in the limit that z is bigger than r, right, this guy just goes like z over z squared plus r squared to the 3 halves. But if z is big, then this goes away, and this just equals z over z squared square root, so this is z to the 3rd, and this is just 1 over z squared. So yes, it does go like 1 over z squared in the limit. All right? So why in the world did we go through all this work when we knew what the solution was going to look like beforehand? Well, we didn't know we only knew an approximation. So if we're close to the ring, we actually have to use this exact formulation. And more so, what if I had a problem where instead of the full circle, I just had half a circle? If I just have half a circle like this, then of course there's going to be a net force in this direction and in this direction, or a net electric field, right? I should be writing this as electric field. Just add another Q in here if you want it to be a force, right? I should have been a little more competent with that. But we realize that that's actually not at all difficult if we know how to write this. So, for example, if instead of a full loop, I just go to some angle alpha, then I'll have this as my actual solution by how long this arc length is. And this is the solution for x, this is the solution for y, and this is the solution for z, depending on the arc length, right? So once we know how to do the vector calculus, let's get back to the paper here. Once we know how to do the vector calculus, right, then we could do much more difficult problems, right? And really, they're not more difficult, right? Once you've done this, you're done, right? The only thing that's difficult is the integration. But we can use tools to do the integration once it gets hard. All right. So hopefully now you're starting to get a better idea of some of the difficulty, some of the approximations that were kind of hidden from you, right? And again, this is not a bad thing. You have to start somewhere, right? And we often do this in physics. We tell you half-truths, right? To get you somewhere where you can start to understand more and more truths, right? So for example, atoms are the smallest possible thing in the universe, or solid balls. Oh, sorry, we lied to you. There's electrons and protons and neutrons. Those are the smallest things in the universe. We can't deal with them. Oh, we lied to you. There's quarks. Oh, we lied to you. They're not balls. They're actually waves, right? It's just to kind of get better and better understanding, right? And so we're going to get a more thorough understanding, and hopefully this will not only allow you to understand the physics better, but it will also allow you to understand the mathematics better, okay? So, just a little bit of a preview then. This was an introduction. Again, don't feel bad if you don't know how to use the numerical stuff I used. We'll go through that in detail. Don't worry if you don't know Wx maxima. We'll go through that in detail. We'll also go in detail of each of these things I did. The vector calculus, the path integrals, the series solutions. All right? And so what we'll actually start with next time is basically understanding series. So why are they series? We already saw one of the reasons they're important with this pendulum. So this is an important thing, but also they're the fundamental definitions. They're fundamental. Remember, calculus is defined with series. The fundamental definition of a derivative, right, is f of x plus delta x minus f of x over delta x in the limit that delta x goes to 0. All right? So when you took this course, you might have thought, why do we spend so long on doing this? Well, if you go back to that pendulum code I showed you, this is exactly how that pendulum code works, right? This is called Euler's method, and this is one of the things we'll learn is by using this, we can actually make simple time evolution and see how things work. We also use Taylor series expansion, right? So we also know that any function can be written as the sum of the derivatives of that function, right? Over n factorial x to the n, right? So we also use this, right? Again, that's how we knew the pendulum and the approximation and which are the next order terms, right? And when we did the ring of charge problem, right? Remember this ring of charge, it's often that we look at this little finite element, right? And we change from a delta x to a dx, and we change from a sum to an integral, right? So this is what series has to do with everything, and this is why it's usually at the beginning of each course, is because it's underlying many of the concepts we're going to use. All right, so hopefully next time we'll start to get a much more thorough understanding of series solutions, and then we'll go on from there. I will see you next time.